So our next lecture is on gravitational potential energy. This is section 4.3 in your textbook. And what you will recall is from one of our previous lectures about kinetic energy, we talked about the work energy theorem. And that's going to come up again in this lecture and further on in this unit as well. So let's get into this. So we have gravitational potential energy is a term we use for the energy possessed by an object that has been raised to a position higher relative to a lower position. So in this situation, if we have a person with a sledgehammer, the gravitational potential energy of the sledgehammer is higher, or it's greater, the higher the sledgehammer is. And it is lower the closer the sledgehammer is to the reference level. So that note, the greater the height or the mass of the sledgehammer, the greater its gravitational potential energy. Another option is if we have two objects that are raised to the same height, say two objects are raised 10 meters above the reference level, but one of them is a cannonball and the other is a ping pong ball, the cannonball, which has a greater mass, will have greater gravitational potential energy. So here's a slide to copy. Gravitational potential energy is the energy possessed by an object due to its position relative to Earth. It's calculated by finding out the product of m times g, the acceleration due to gravity, times h. And that g, it could change. It's usually 9.8 or 9.81 for a problem that deals with Earth. But if we are on another planet or on another area that has a different gravitational field strength, we would calculate something differently. Now, what you see there for G is the units are newtons per kilogram. The newtons per kilogram is equivalent to meters per second squared. But we treat it as newtons per kilogram for a gravitational potential energy problem because that makes it easier to have units divide out each other. So m, which is in kg, times g, which is in newtons per kg, gives us just an n. So let's look at gravitational potential energy and work. So imagine we have a mass that's being lifted at a constant speed, so there isn't a change in its kinetic energy. The only energy the mass will gain will be due to its position in the gravitational field. So the higher it is, the greater its energy. So since work equals force times the displacement, and F equals m times g, and displacement is basically the difference between the final height and the initial height, then we can rewrite this equation as W equals, replace the F with an mg, and replace the delta D with an H minus F, or sorry, HF minus HI, and we're left with mgHF minus mgHI. So work is the change in gravitational potential energy. So the work done in raising an object is equivalent to the change in its gravitational potential energy from its final position to its initial position, or its initial position to its final position, rather. So in this case, when the velocity does not change but the object's position changes in height, the work done on the object is equal to the change in the gravitational potential energy of the object. This is another example of the work energy theorem. So work can be written as the change in the gravitational potential energy. So this slide I'd like you to copy, the work energy theorem. Work is equal to the change in the gravitational potential energy, and then it's written in two other ways that you can see there. So let's look at a quick little problem here. If we have a gas-powered winch on a rescue helicopter, and that winch does 4,200 joules of work while lifting a 50-kilogram swimmer at a constant speed up from the ocean, what height was the swimmer lifted? So if we can imagine this as work equals mgh, so our work is 4,200, and we have to solve for h. So divide that 4,200 by our m, which is 50, divided by our g, which is 9.8. We're left with 8.57 as our delta D, our change in height. And we have to round that for two significant figures, and we get 8.6. Here's a weightlifter lifting a barbell 2.2 meters up. The lift increases the gravitational potential energy of the barbell by 490 joules. Determine the mass. So on the left side of our equation is 490. That's work equals mgh. So the work is 490. The m is unknown, but the g is known to be 9.8. The h is 2.2. That's the change in the height. So our m is 22.72, or when we round for significant figures, we get 23. Next problem, we have a 2.5 kilogram piece of wood that falls onto a carpenter's table from a height of 2 meters above the table. So calculate the kinetic energy of the wood as it hits the table. So we have to recall that as our object kind of falls, the gravitational potential energy turns into kinetic energy. So let's find out what the gravitational potential energy of the object is. It's m times g times h. That's what its height was. So its gravitational potential energy is 49 joules. So the kinetic energy at the end of its fall would also be 49 joules. That's because all of that potential energy has turned into another form of energy, which is kinetic energy. So now we have to calculate the speed of the wood as it hits the table. So the equation we're looking at here is EK equals 1/2 mv squared. So EK is 49, 1/2 m, we know the m is 2.5, and the v squared is what we need to solve for. So we'll take that 49, we'll multiply that 49 by the 2, which is the 1/2 on the other side, divided by the 2.2 kilograms, which is the mass, and then we have to find the square root of this. That gets us to 6.26, and looking back at our equation, or our original question, we had two significant figures, so we rounded to 6.3 meters per second. Now, that situation we gave is kind of an ideal situation where all of the potential energy turns into kinetic energy. But in reality, very few processes involve changes in kinetic energy only or potential energy only. Real processes usually involve more than one form of energy. For example, if an applied force does work on an object so that both its kinetic energy and its various forms of potential energy change, then the work done by the force equals the total change in both the kinetic energy and the potential energies. So that work is equal to the change in kinetic energies plus the change in potential energy. So I'd like you to try the gravitational potential energy problems in this section. And again, if you have any questions, feel free to ask me on the course website or via email.